Не бойтесь, niente.
Hello, everybody.
Hello.
Thank you. Of the homeworks, due dates. Homework 10 due on Monday. No, sorry, Wednesday. And homework 11 is due on the next Monday. I suppose. Yeah. And the last homework is due on the last day of the class. Regarding the quiz problem, if something is going in circular motion, let's say this is the top of an object that's moving in about an axis that's coming out of the board. So that's a direction showing a point inside a circle means it is coming out of the board. And the question was to show the direction of certain quantities. First was angular displacement. So this is angular displacement. The direction is coming out of the board. Even though the angle, it's a magnitude of that displacement will be given in terms of this. That will be delta theta, but its direction is coming out of the board. Same thing with angular velocity. It is coming out of the board, so that's omega. This is also delta theta, so that's coming out of the board. Omega is coming out of the board. Linear or translational velocity. If it's going in a circular orbit, translational velocity. That's tangential. So that's your velocity v. If we have omega coming out of the board, and that's your radius r. Right? So this will be omega, and that's your radius r, and that's your velocity v. Right? So we're talking about velocity v here. Notice v is omega crossed with r, where r itself is the position of the object with respect to the axis. So it's the distance from a line, not a distance from a point. So that's translational velocity. And then there were questions on acceleration. So if it was centripetal acceleration, that's always towards the center. So the same circle drawn again. So centripetal acceleration is towards the center. And that's radially inward. So AC is radially inward. There's translational acceleration, a tangential acceleration. I think that's the better way of word for it. Tangential acceleration. AT. That's that would be alpha crossed with R. And that's in this that's a tangential acceleration. And we also have Coriolis acceleration, which I haven't discussed in the course, but it's a good thing to know if you're interested in the motion of hurricane and other wind directions. It plays an important role. So that's Coriolis acceleration. Coriolis acceleration has the expression omega crossed with R. This is already in the tangential direction, so you have to get omega crossed with the tangential direction, so that's radially inward. So let me just say it is radial. It depends on in what direction are you moving. So let's say just it's radial. So that clarifies some of the directions involved. And we want to go in the same spirit. We want to have an idea of cross product. And this time we want to talk in terms of force, angular force, which we will call is torque. So summary here. So notice time remains the same. There is no difference. There is no angular time versus translational time. But when it comes to displacement, we have delta x or delta x, and here we have delta theta. So angular displacement. This is linear displacement. Then we have the x by dt or velocity. We have theta dt or angular velocity. Angular displacement. And second derivative of angle, that's angular acceleration. Exactly like we have second derivative vector of position with respect to time as acceleration. So that was what we did in kinematics when we were working in one-dimensional motion or projectile motion. We were working with velocity, acceleration, displacement, and time. From that point on, when we started working on Newton's law, there were two concepts that came in. One was mass. And let me mute. Okay. So there were two concepts that came in. Yes, it's visible in the board. That's mass and force. Force was, both were intuitively introduced. We did not very well define them. And you can say there was an acceleration which we consider as the motion. What helps the motion is the force, and what resists the motion is mass. We call it the inertia, right? How much does something help in the motion? It is given by the force, and what resists the motion is the mass. We introduced the idea m here, and the force a vector quantity. Right? So this was not mass, was not a vector, but force was a vector. We would like to have the idea of angular force here, and that will be defined as torque, and that's what we want to do today. So it's torque. And when it comes to mass, we will see that this will be called moment of inertia, or let's call it angular inertia. Or sorry, rotational inertia, right? So this is inertia to translational motion. So this is rotational inertia. It is also called moment of inertia. Is it visible? Nope. So that's moment of inertia. This will be represented by the Greek letter tau. So that will be a vector. Again, we will keep our axis to be in the same direction. So this will, the vector nature will be either positive or negative. We won't have to worry too much about how things are moving. And here, the letter we will use will be I. So we won't talk about moment of inertia or the rotational inertia today, but that will be on Friday. But today we want to talk about torque. This will be given in terms of the vector product or the cross product. So let's quickly review that. So this is the vector or the cross product. Of two vectors, A and B. So that's A crossed with B. Let me write C is equal to A crossed with B. The magnitude of the vector C, let me write this as magnitude, or often we just write, whenever we don't write the vector sign on top of it, that means it's a magnitude. That's equal to A times B, the magnitude of A times magnitude of B, times the sine of the angle between the two vectors A and B. So let's say this is a vector A, and that's vector B. And the angle between them is what is relevant. Notice that it is necessary that the two tails of the vectors come together. By any chance, if they're not, then you want to move them accordingly. For example, if this was vector A, and if I were to draw vector B in this manner, that's also the same idea in there. In that case, you want to see the vector or the angle as the angle between the two vectors. That means to say, if you were to have this vector moved such that the tails are at the same point, and it is the angle between. That's your magnitude, length of vector A, length of vector B, times the sine of the angle between them. And there is also a direction. is given by the right hand rule. And the right hand rule is got using the right hand rule. You typically often most of us write with the right hand, and in that case it's tempting to use the left hand, so don't mess up on that. Use your fingers to point in the direction of A, and then you have some freedom. Place your palm in the direction of B, open your thumb, and that's the direction of C. So you have, in this way of saying it, its fingers is A, palm faces B, and thumb gives you the direction of C. Okay, that's the procedure to get your A cross B. We want to talk about torque now, or what causes rotational motion, what helps rotational motion. So let's introduce the idea of torque, and let's motivate this a little. So let's think of opening a door. So this is a door, a cross section of a door. Think of this is the axis of the door. So that's your axis, and the door is free to move around, right, about this axis. This is a top view of the door. It can rotate about the axis. If you want to open the door, we will typically push on the door at a farther point. From experience, we know that it takes more energy to push the door. Think of this as a heavy door. If you were to push it at a closer point to the axis. In fact, it is clear that if you were to exert a force on the axis, the door is not going to open, right? So we all know this, maybe very early in life when we are still children, we learn this very quickly. So if there is any rotation needed, if you were to direct it in the direction of the axis, there will be no motion. So this will cause no rotation. So we want to capture that fact. So that's example, let's say 1. Let's do another scenario. If I have the same door again, the same axis, right? And if I were to now push on this in this direction, right? So I exert a force in the direction such that force is pointing towards the axis. Again, there will be no rotation. And we want to capture these facts, right? And anything that is not causing rotation is also important. So we should have a rotational force, which is we are defining to be torque, should be 0 in that scenario. So we want to have a definition of torque which incorporates these facts. Third is, if you were to exert a force at an angle, so now let's say I exert a force, the same amount of force in all these places. Let's say this was a force, and I exert it at an angle theta with respect to the direction of the door. In that case, there will be less motion. So let me again have a fourth diagram. Is this still in the picture? Yes. So the same door again, axis, but this time if I were to do if I were to exert the same force in a perpendicular direction, then this is more torque versus this. So this is relatively less. less torque. And let me finally put one more scenario, and that is that if I were to exert the force somewhere closer, keeping it at 90 degrees, if I were to exert the force, let's say half the way of the door, this will be relatively less Q. And you would like to define the idea of rotational force or rotational torque that incorporates all these facts. So we will define our torque to take care of all this. And let's go back to 1 and let's define our torque as. So torque will be defined as R crossed with F. What is R? What is the force F? So we have the idea of force very clear. We have used it sufficiently. And let's now define what is R here. R, typically we have been using this for designating the position of the object. Yes, this can be the position of the object, but this time it is the perpendicular distance from the axis. So this will be the perpendicular distance from the axis, which means that the definition of torque is dependent on the choice of the axis. In our scenario, most of the times we will choose the axis to be passing through the center of mass, but in general, it doesn't have to be such a scenario. But once you have a line given to you, you can define a distance of another point with respect to that lines, and that's perpendicular to the line. So that's your vector R, and this is torque, which gives us the idea of rotational force. So let's calculate the torque for this. So torque is equal to, in this case, notice R. What is your R here? R is the distance from the axis. Wherever you're exerting the force, how far is that from the axis? In this case, you're exerting the force on the axis itself. This is equal to 0 because R is equal to 0. So no work needed. If the vector R is 0, you immediately conclude that that's equal to 0. What about the second scenario here? In this case, R is equal to, so this is your, let's say the length of this door is L. Let me say number, right? So let's say 1 meter, right? So it's 1 meter. So, and let's say this is your X direction. So vector R is 1.0 times I hat. And the force could be, let's say this is 3 newtons. So that's minus 3.0 I hat. So what is happening here is vector R is in this direction, and force, so that's your axis, and the force is in this direction. So if I move these forces accordingly, that's your axis. Relative to the axis, that's your R. Force is exerted inward. I moved the direction or the position of the force. It's actually exerted here, which decides what your R is. But once I put it like this, it's clear that this is 180 degrees. The angle between them is 180 degrees. So torque is equal to, let's say the magnitude of the torque is equal to 1.0 times 3.0 times sine of 180. But sine of 180, like sine of 0, is equal to 0. So this does not contribute. Notice neither of the vectors is 0, but since they are oriented in a certain way, the torque comes out to be 0. So that's a non-trivial feature of a rotational force, that the distance comes into picture. Not only the distance, in what direction you exert the force matters. In this case, now torque would be, so that's L, so the same, let's say this is L, so that's your L times F times sine theta. And if the angle was 45 degrees, it will be less than if it was 90 degrees. Sine of the sine function is maximum for 90 degrees. What is the direction here? So let's say the direction of the torque. So this is your torque vector, and its direction will be r crossed with F. R is in this direction, force is in this direction, so it's coming out of the board, so that's n hat. So n hat is in the direction of coming out of the board. What about here? This is torque is equal to L times F. Now it is sine of 90, and sine of 90 is 1. Sine of theta is always less than 1, and sine of 90 is 1. So that's the maximum value it takes. So that's L times F times n hat. So the best way of opening the door is to exert the force at the extreme end of the door and perpendicular to the door. That's why you have the door knobs on the extreme end of the road. You typically don't see door knobs attached to the center of the door, right? So it's much more less work or less amount of force to be exerted in that direction. And then hat here again is in the is coming out of the board. If it was closer to the axis, tau will be, let's say this was L over 2. So that's L over 2 times the force F times sine of 90 again. So as far as angle goes, we are getting the maximum possibility, but since we are exerting the force closer, it reduces in size. So that's LF over 2 times n. So that should give you a sufficient idea of the definition of torque. So radius, how far you're from the axis, does help your motion as far when you're exerting a force F. If we want to discuss motion, we have to introduce the rotational inertia also, but let's consider problems here which actually does not cause motion. So that is the idea of torque coming in, but we won't make it move because we still don't have the idea of rotational inertia. So these are broadly called problems on statics. Often you will take a complete subject on statics, or you can say static equilibrium. So this is the very simple cases in statics. So let's do some problems here. So example, so the simplest example could be where we have a seesaw, right? So let's call this a C. So this is a game, or you must have played on this. Is you have a plank which is, let's say, uniformly distributed so that its center of mass is right at the center, and there is a fulcrum here, so just an object on which this can balance. If everything was perfect, this would balance here horizontally. So that is a mass m let me remove the fulcrum from there so that I can draw the forces. That's your center of mass, and the mass of the plank acts down at this point. So that's the mass of the plank. Let's call it capital M, and that's mg. Let's say there is a kid who sits on the extreme end of the plank, and there is a gravitational force m1g acting on this kid. Let's say the distance here is L, and that's also L. And let's have, this is a, let me have M to be about 100 kgs. It could be a light plank, it doesn't really matter. So let's say about 20 kgs. M1 could be about 35 kgs, and let's say M2, who is heavier, has a mass M2 is about 60 kgs, 65 kgs. It's clear that probably intuition, if you're not familiar, if you were to sit right exactly at L, the left-hand side will be significant, the torque will be significantly larger. So you would have to balance it by sitting closer. So that's the idea. So the idea question is, if L was equal to 1 meter, how much should X be equal to? So that's your axis. So that's your, and at this point, I should say that it's not very obvious what your axis should be in a problem involving statics, because there is no motion, right? So if there was rotational motion, you know about what point it is rotating. If it is not really rotating, you can calculate the torque about any axis of your choice. So you could pick any line and you'll be good. But center of mass typically is a good choice. If you have a confusion, pick center of mass. That's a guide for you. Otherwise, in statics, you can actually choose it however you want to. First, let's go to Newton's law. So this is a linear motion. We know that mass times acceleration of this whole object. So acceleration is 0. So that's equal to 0. So that's equal to m1g plus m2g plus the capital Mg. And if all three are pointing downwards, something has to balance it. So that's a normal force, right? Which will be exerted on the center of mass, right? Plus the normal force. Oops. Plus the normal force has to be equal to 0, which using the directions, we immediately conclude then that n is equal to m1 plus m2 plus capital M times g. And that tells us 60, 90, 100, 120 into 9.8. Let me finish that.
Shouldn't n be negative in that case?
I moved it, right? So this will be negative, that will be positive, but then I moved the n to the left-hand side. Clear? Now?
But everything's being added on the side where the other side's just 0.
Yes, so that's...
So how can you don't change the signs at all when you move n to the other side?
So this is minus m1g minus m2g minus capital Mg plus n. That's equal to 0. Correct?
Okay.
And then you move this to the either, how do you say this? Yeah, move this to the left and then flip it, correct, somehow. N is equal to M1 plus M2 plus N times G. And that's 120 times 9.8. So that's what we have done before. So that's not dealing with rotations. Let's finish that off. So that's 1176. There's 2 sig digits. So that's 1200 newtons. Okay, that's good, but we would like to now do torque, right? So similarly, so as far as the torque equation goes, we have no rotation, so that's 0. So mass times angular acceleration actually, but we haven't introduced that idea yet. So this is no rotation, so that corresponds to 0 on the left. In the next class, we will talk about how we can make this non-zero and actually have rotational motion. And there are 4 forces now. So each one can exert a torque. So there's torque due to the first mass. There's a torque due to the second mass. There's a torque due to the mass of the plank itself. So let me call it capital M. Plus the torque due to the normal force. Each of these forces can exert a torque. Move this way. Sure. Okay. Again, we have this diagram. So that's your M1G. That's your center of mass, capital MG, the normal force, and that is M2G somewhere here. Right, that's your forces, that's your L, right? This length is L. Let's begin with what's the torque due to the normal force. We have to look for R crossed with F, right? So this is R crossed with the force, which is the normal force. R here is the distance between the axis and the point where the force is exerted. So it's important where you draw the vector. So the normal force acts on the center of mass, which is right here, and the axis is also the center of mass. Like we choose our axis to be the center of mass, so that's 0. So R is 0. Distance from the center axis that we chose to be the passing through the center of mass and coming out of the board, and that's equal to 0. So torque due to the normal force is immediately 0. What about the torque due to the Planck mass? Same thing. The distance, remember again, the masses act on the center of mass of the object that we are discussing. Here, the object was the Planck, and we said it is uniform, so it is actually right at the center. So that's the center of mass of the Planck. So that's R crossed with capital Mg. Again, this is equal to 0. So that's equal to 0. So 2 of the torques are gone. Now we have torque due to the M1G here. So let's do that. So that's your axis. That's your position this time. So that's your R. And that's your M1G. Okay. So torque due to the first force will be the length of this vector, so which is L, right? So that was L. The length or the magnitude of this force, that's M1G. And the sign of the angle between them, you have to move this way, that's 90 degrees, or you can pick this angle. So that's 90 degrees, which makes that 1. And now the direction, or you point your fingers in the direction of our palm is pointing M1G, and then you open the thumb, it's going into the board. So that's minus Z, let's say. So that's minus K hat. So K hat is, so if this was K hat, so the direction of the axis coming out of the board was K hat. So this is minus K hat. And that's equal to L was 1, so that's 1, M1G was 35 kg times 9.8 times 1 times minus K hat. So that's equal to 35 times 9.8. So that's 343, I can write it here itself. That's 343 or 340 in 2 sig digits. Now what's the unit of torque? Torque has a distance and a force. So it is Newton times meter. That's a unit of torque. Coming to the other, oops, too much down. Coming to the torque due to M2G, so this was X here. So let's draw the axis again. Maybe erase this. So that's your axis. And this is the distance now, R. And M1 or M2G is acting down. So what's going to be different in this case? Torque due to the second mass. R this time is minus X, sorry, X, and yeah, let me get the directions using the right hand rule. So it's only the magnitude that is coming up. So that's X, M2G, and then the sign of the angle between them, again, to this. That's 90 degrees, right? Or move this M1G here, so the angle between them is sine 90. So that's sine of 90, and the direction now, again, use the right hand rule, pointed in the direction of our palm facing M2G. This time when I open my thumb, the thumb is coming out of the board, so that's plus K. So that's plus K. And that's equal to M2 was 65. So this is 65 X times 65 times 9.8 times 1.0 times K hat, which is equal to so that's 65 into that's 637 X in the K hat. So X has to be determined. Now here is the Newton's law for rotation. All the torque has to be equal to 0 since this is not moving. So like all the forces has to be equal to 0. Torque 1 plus torque 2 plus torque due to the normal force plus the torque due to the plank has to be all equal to 0. That means to say these two are already equal to 0. So we have 0 equal to torque 1 was 340. Oh, I messed up there, right? So when I wrote 340, I should write the direction, right? I did not write this. So this is minus K hat. So let me write that as minus 340, and without the units, that's K hat. And the torque due to the first force is 640 X in the direction of K hat plus 0 plus 0. This whole thing has to be equal to 0, and this is a vector equation, but all the directions are the same, and that would be a common feature because we are doing simple problems here. That would be the challenge usually, as to all these vectors doesn't have to be in the same direction. That's because our axis is not moving around. So this leads to 640x is equal to 340, and that implies that x is equal to 340 divided by 640. And that's 0.53 meters. So, so the heavier object or the adult doesn't have to be sitting that far. If this was 1 meter, it's about halfway down, right? So that's 0.5 meter. And we learned this from experience, that if you're heavier, you try to balance. And this is how a physical a chemist, the balances that we see in chemistry labs work, right? This does not use the idea of a spring, and that gets rid of the dependence on this G. So all the G's actually cancel out. If you notice, even though we used it, G actually cancels out in this whole equation, and that makes it independent of the gravitational acceleration due to gravity. There's 5 more minutes. I'll start on a problem, and I won't be able to finish it, but I'll give you the ideas. So this is also related to an example in your homework. So let's think of a plank, so that this could be a table. So that's a surface, that's another surface. This could be the rooftops of 2 buildings also, however you want to imagine it, or 2 tables. And let's keep a plank here, which is not exactly centered between the two roofs, let's say, or 2 tables. So the center of mass, assuming that this is actually uniform, will be down there. Right? So that's your mg. And there will be normal forces exerted here. So there will be a normal force exerted down there. So that's N1. And it's not very obvious where the normal force will be. It will be since there is a contact force in here. So let's have this surface slightly, you keep a weight in there so that all the force is pointed at one point. So this is a small object, you kept it in there. In that sense, so N1, N2 will be exerted here. That's just making the problem a little simpler. So that otherwise you have to worry about where the normal force is acting on the left-hand side. And one could ask, what are the normal forces? And you immediately would say, okay, if we use Newton's law, the standard Newton's law, we would say N1 plus N2 is plus mg is equal to 0 because it's not moving, right? No acceleration. And if you were to put in the directions here, so we have N1 plus M2 is equal to mg. Because mg is pointing downwards, it's negative. Let's say m is given to be 150 kg. So we know the right-hand side, but we don't know N1 and N2, and we might say, oh, we cannot get this because there are 2 unknowns. But if we know that the torque also has to be balanced, so the torque due to 1, torque due to the normal force from 1, plus the torque due to the normal force due to the second normal force, plus the torque due to the mass is equal to 0. That's the 3 forces acting on it. If this was a center of mass, if we choose our axis to be this, so that's your axis, choose that to be the axis, then the torque, because it is acting right at the point, right on the axis itself, this will be 0. And let's say now there is a x1, so this is x1, that's your x2. That's your distance from the edge of the table. And we can see that this, if you work this out, n1 times x1 will come out to be exactly equal to n2 times x2 in this scenario. So if you know x1 and x2, you can actually calculate n1 and n2. So let me combine these two. And if you're given, given x1 and x2, we can find, determine n1 and n2. I'll elaborate on it when I'm making the solutions, but it's pretty much the same ideas goes through. You just have to combine those equations. So I'll leave that to you guys because the time is up. Thank you and good luck.
Have a good rest of the day.
You too, Blake. Thanks.
You're welcome. Thank you too.
Bye. Let me end the meeting.